Swayam Prabha. Digital India. Educated India.
Once again, welcome to this soil mechanics course. As I have mentioned that in the last lecture, that we have to understand certain characteristics, that is permeability characteristics, compressibility characteristics and shear strength characteristics. Okay. So, that will come of course much later, and before that we have to understand the composition actually. So, like we have mentioned rock formation, then soil formation. Now, the soil in what form? As I have mentioned that by different agencies different types of soil can be formed, and again sometime the we understand this sand is one type of soil, that is based on size, clay is another type of soil based on its size, silt is another type of soil based on its size. But now, in many condition or situation they will be mixed together. If I take a soil mass from if I take soil mass from any site, always you will find they consist of all three particles mostly. Most of the time will have all three particles, that means it may have sand, it may have silt, it may have clay, or sometimes it may have silt and clay, sometimes it may have sand and silt, like that. So, that means you have to understand now the composition. If you understand and if you know the composition of soil, many things you will understand actually. You may not be able to quantify that how strong it is or how permeable it is or how compressible it is, but at least if I know it is a sand, it is comparatively less compressible, it will be comparatively stronger, and it is comparatively more permeable. Whereas, if it is a clay soil, then obviously and clay silt together, then we will understand it will be compressible, highly compressible, and it is actually strength is comparatively less and it is comparatively less permeable. So, these are qualitative information, that means if I know size or composition, then we can get those qualitative information. So, because of that we need to if I get a soil from a site, and then what I have to do first, I have to see the grain size, then what size of particles and what quantity is present in a mass, and if I get that I will be able to tell qualitatively many things about its behavior. So, because of that soil classification is the first step perhaps in soil mechanics course. Whatever we have got, those are introductory actually. The classification perhaps is the first step. That means, if I want to develop a site or develop certain things in a particular area, first of all you do field visit etc., and see whether it is a rocky soil or sandy soil or clayey soil or all those things, you find out, select the site, and after selecting the site, then next step is the sampling, then testing. Testing means what? What test is first is the classification, that means what particles at what composition, what proportion is present. So, that to be first determined. So, for this actually in fact we have to, for classification purpose we need to do some test, and there are different tests in the laboratory, you can do it. But suppose you are now in a site and you do not have any equipment or instrument or accessories with you, but you have to give some qualitative idea what type of soil it is. So, in the field itself sometime we may able to do some sort of test, and this qualitative actually obviously, and then I have kept in this table that sand, silt and clay in 3 column, and you can see that, and side by side what I will look at. And if it is sand, then individual particles are visible, that means sand obviously we can very easily can differentiate, because those particles if I take in hand and if I this like that, then it will be flowing from my hand. And silt also, some particles are visible, generally not visible, but it is finer. So, it is particles are not visible generally, but some particles may be visible, whereas in clay no particles will be visible. So, this first step, if particles are visible, then definitely sand, and particles not visible, it can be silt or sand, something sand, silt or clay, this much. So, one test, physical test we do. Then exhibit dilatancy, this is another thing between your sand, silt and clay, there will be distinct difference. We can say, we can make a soil, we can take some amount of soil mixed with water, and you make a soil pat on your hand, and then if you shake like this, and then finally, if the water comes out on the surface and becomes shining, then that is called dilatancy, exhibiting dilatancy. That means, sand and silt both cases actually we will see that. That means, now, and whereas in the clay no dilatancy will be visible. So, that means, now if you see individual particles visible, then you can find out this is a sand and exhibit dilatancy, and sand can have exact dilatancy, silt also can have dilatancy, but silt particles are not visible. Then in that case, again we can differentiate between sand, silt and clay. Clay does not have any dilatancy. So, first two steps by and large we will be able to differentiate what is sand, what is silt and what is clay. So, physical examination or checking is visible, is individual particle visible, sand is almost identified. Now, if the silt particles are not visible, it can be either silt and sand, silt and clay. Then if you do dilatancy test, then silt will show dilatancy, whereas clay will not show dilatancy. That means, whether it is silt or clay, that can be differentiated. Now, further still if you have doubt, then that the sand will be easy to crumble and falls off hand, like if I do like this from my hand, easily it will go out of my hand. So, easy to crumble and falls off hand when dry. The wet condition of course, few particles may stick to my hand, or otherwise if it is dry condition, if I do like this, sand will go out from my hand. Silt also same, easy to crumble and can be dust off. That means, silt if I want to clean from my hand, I have to do like this. Until unless do that, silt sometimes some of them will be stick to my hand, and it is easy to crumble and it can be dusted off my hand. The silt generally whatever dust stick to my hand, then if I do like this, it will be dusted off. Whereas, if it is a clay, hard to crumble, that if I take a piece of clay, then it will be dry, it is difficult to break, and if it is a wet condition, then it will be stick to your hand. So, it will not be easy to dust off also, when it is so fine particles, it will be sometimes stick to your hand. And then these are the three, then third, fourth one is feels gritty. When the sand particles you rub between your finger like this, you will feel gritty, that very rough, and if it is silt also will feel rough, and gritty and feel rough, this difference actually only through experience one can develop, that what is gritty and what is rough. The sand, what is very rough feeling will be there, whereas silt will have some feeling, but it is not rough as it is in the sand. And whereas, if it is a clay particles, like if you take some amount of kaolinite or illite or montmorillonite and put between the fingers and like that, very smooth like talc and all similar to that, feel smooth feeling will be there. And last is another is sand will not have any plasticity. That means, sand mixed with water, you will try to make ball, you will not be able to do that. If you cannot do that, that is definitely it is a sand. You cannot make a ball, or it cannot roll and in a thread, like you cannot roll into a thread. And silt, whereas may have some but plasticity. So, you can mix with water, you can make a ball, but it is very easy to break, it cannot make big ball or something. Some plasticity is there, because of that you will be able to do, you will not be able to make a very thin thread, you may make a very thick thread you can make. Whereas, if it is a clay, then if you mix with water, then you can make any ball, any shape, like our some clay modeling etcetera. Why we can do, we are able to do, because it has plasticity. Because of this plasticity, we can give the different shape. So, in the field, if you are there, that means field identification, this is a field identification I am talking about. That means, at a site actually, suppose as an engineer, that site what type of soil is present, if you want to identify, then these are the few checklist you do, where you can whether particles are visible or not, then you mix with water and make some pat on your hand, shake it like that. If water comes out, then either it will be silt or sand. If it is not there, then it is a clay. Then if it is take a small mass, it is easy to crumble, then it is a sand. It can be silt also, but silt sometimes some soil will be stick to your hand, whereas sand nothing will be there in your hand. Sand easily will fall off, and when it is salt you have to dust off, and when it is a clay it will be stick to your hand. And when it is sand, if you rub between your fingers you will feel gritty. When it is silt, when you rub between fingers, it will be your rough feeling little, and whereas when it is a clay it will be smooth feeling. And sand does not have plasticity, and silt will have little pulse plasticity, and clay obviously having high plasticity will be there. And because of this plasticity property, you can make any ball, any shape, and you can make thread also quite thin thread. So, these are the small things if you do at site, then you will be able to identify whether that the site sand is present, silt is present or clay is present. So, this is actually, as I have told, that the physical identification, but that identification no one will accept until unless when I have taken a job of classification job, and if though I know by that physical test that it is a sand or it is a silt or it is a clay, but if I give that information to my client, they may not accept that. They want some data, they want some chart, plot, and on based on that I have to conclude that this is a sand, silt or silty sand, something like that. So, for that actually to give or do some analysis, that is actually inspection, physical inspection, and if you want to do some analysis, there are mechanical analysis, it is called, or sieve analysis, or it is called dry analysis. That means soil will be there, you collect from the site, and then if it is a granular soil suppose, then this can be done, analysis can be done through sieve analysis. And this sieve actually different countries will have different types of different size of sieves, and India also will have a set of sieves which we use in the soil mechanics, and they generally 4.75 millimeter size of opening is the topmost sieve, and 2 millimeter size is the intermediate, 1.18 millimeter next, then 600 micron, 425 micron, 300 micron, 150 micron, 75 micron, and the bottommost is the one pen will be there. So, this is the number of them are here. This is the suppose topmost is 4.75, and in between suppose it is 2.2 millimeter, this may be 1.18 millimeter, this 600, then 425, and then maybe 75, in between there may be 1 or 2, and this is the suppose pen. So, a definite amount of soil to be taken from the site, or whatever sample collected from the site, around 300 to 400 gram sample can be taken and can be kept on the topmost sieve, and after putting on that sieve, and then it has to be all sieve will be kept one above another, and then finally, this can be shaken by hand like this, or nowadays it is there is a motorized shaker. You can put the shaker entire assembly in the shaker, and then you can give certain amount of fix the time that how long it has to be shaken. When it will be shaken by vibration, then the opening this whatever we have mentioned, this 4.75, 2 millimeter etcetera, they are actually the opening size. So, if the soil particles is bigger than 4.75 millimeter, it will retain on this, and if it is smaller than that, then it will pass through this. So, like that each sieve some amount will be retained and some amount will be passed through, and finally, each and every sieve the certain amount will be retained, and finally, bottommost sieve, that is 75 micron sieve, some amount will be passed through and some amount will be retained. So, this pass through material will be collected in a pan, that means there is no opening. So, it will be collection only, and if it is a sandy soil, the passing through 75 micron will be very nominal amount. So, that is collected here, and if it is 300 gram of soil, you have to finally collect it from each sieve, the amount of soil retained, and they are individual weight will be taken, and finally, what is collected in the pan has to be taken, and finally, all to be added, and you have to see that the total amount is about same, maybe very fraction loss can be there because of many things, one grain can be lost here and there, but if it is too much loss, then this has to be repeated. Otherwise, whatever amount we have taken originally, and finally, soil retained in each sieve including the pan has to be the same. So, this is the way actually mechanical analysis will do. That means, we will take a certain amount of soil, put it in the topmost sieve, put it in the shaker, and then after a definite amount of time shaking, the soil or particles retained in individual sieve to be collected and weighed, and that has to be tabulated. This is the tabulation will be done like this. Sieve size I have written here, you can see again 4.75, 2.4, 1.2, 600, 425, 300, 150, 75 and pan, and you can see around 300 gram of soil is taken, and you can see retained on 475 millimeter 4.75 millimeter sieve is 11.02, then retained on 2.4 millimeter is 30.45, like that. Finally, on the pan retained is 7.24, and if we add them, you will see it is coming 300. So, for calculation purpose or classification purpose, what we do? First table is the sieve size, and or sieve size is nothing but equivalent to particle size, soil particle size. If the sieve size is 4.75 and if it passed through the 4.75, then particle size is smaller than 4.75, or the particle retained on 4.75 millimeter, that means the soil particles is bigger than 4.75 millimeter. So, that is what a first column. Second column will be weight retained, all individual pan, and then third column to be prepared, that is cumulative weight retained. So, that means here cumulative retained will be same as the previous retained on 4.75, but when I will go to the next stage, the cumulative weight retained will be the weight retained by 4.75 millimeter, weight retained by 2.4 millimeter. So, these two together, these two will be added and this will be there. Now, if it is cumulative retained for 1.2 millimeter, so these three to be added, then cumulative retained in 600 micron, then this 4 will be added. So, like that finally, cumulative. So, when I will go to the pan, that added all amount, then it has to be 300 gram, because we have taken 300 gram, sometime a minor fraction will be less. Now, after getting cumulative weight retained, we have to find out cumulative percent retained. So, you can see initially was 300 gram and cumulative retained 11.2. So, percent if you calculate, it comes 3.67, and it was retained 40 cumulative percent retained is 41, cumulative retained is 41.47 and total was 300, this by this percent retained will be this 13%, 41 out of 300 is 13%. Similarly, 292.76 at this level cumulative weight retained, then percent cumulative retained will be this by this. So, 97%, and when you will go it becomes 100%. Now, percent finer is or percent passing, percent finer nothing but percent passing. So, through 4.75 micron how much percentage is passing? 100 minus this. So, this is the percent passing through 4.7, that means 96%, 96.33% of soil taken out of 300 gram is finer than 4.75 millimeter soil particles. Similarly, here if I see the 86.18% is finer than 2.4 millimeter soil particles. Similarly, 70%, 70.76% is finer than 1.2 millimeter. That means, through this sieve 70% will be passed. So, like that finally, size and percent finer. So, in between we have done some tabulation. Finally, we will be using this column versus this column, that means this column versus this column, that means sieve size versus percent fine or particle size versus percent fine, and particle size will be plotted in a log scale and percent fine will be in the normal scale, because by this only people started studying and streamline some behavior or classification process, which is the same we are using. So, So, typically now as I have mentioned that if I one side, as I have told you that you have to use percent fine by weight, and this side is the particle size and log scale. You can see 0.01, 0.1, this is the log, say one cycle, this is another cycle 0.1 to 1 and 1 to 10. So, like then whatever we have got the previous table, whatever we have got, that is sieve size versus percent fine, and if you plot, this is not the corresponding plot, this is a arbitrary plot I have taken, that is only to show how to do the calculation, and here I have shown the plot, how plot looks like. So, if you collect soil from different site, the plot will be different, and based on that shape of the soil, shape of the graph, one can actually tell many things about the soil grain composition, and you can see this, if it is a typical S shape of curve we get, it typically looks like a S shape curve if you get, then that means actually all particles almost present almost uniformly similar way, and because of that, that is called well graded. That means all particles are same quantity is present. So, that because of that we can say that is a well graded, and whereas if a curve, if you find only this portion like this, the curve is like this, that means only a particular size is present in this soil. So, if the curve is like this or curve is like this, then that means a narrow range, only a particular size of the particle present in the soil mass. So, because of that, if this type of curve if you get, that is called uniform soil or poorly graded soil, whereas if you get this type of curve, that is proper S shape, that means you get, that means all size particles present, then that is called well graded soil. In fact, in the civil engineering purposes, in real life, in fact, if we say we feel that uniform means good, everywhere we expect uniformity, whereas in the soil mechanics, soil is uniform means it is not at all good sign. Uniform soil is a bad soil, because only one particular size of the particles are present, that is why it is called uniform, and when all particles are same size, then voids will be more. Like if it is same size of sphere if you stack in a particular space, then amount of voids present in that, and instead of that if I take a different size of sphere and put it in a particular place, then voids will be reduced significantly, because between the bigger particles smaller particles will enter and amount of voids will be reduced. So, like that if it is a uniform soil, that means same particles are present mostly, then voids will be large, and because of that the soil is not good. That is a uniform soil here, no good. If it is a well graded soil, that means all sides present equally, that is well graded, that is actually good. So, that means once you do a test from a sample and get this gradation curve, and from this what we can get, whether soil is good, bad, and what soil present at what percentage, all those things we can find out. And in fact, from this curve if I want to find out from the, we have a certain number of sheaf size, but still I want to find out suppose what is the percent soil is finer than 0.1 millimeter size. So, this is 0.1 millimeter I have marked here, I go to this curve and from here I can see the percentage is more than 40%. That means, for this curve the particular soil, that means near about 45% is finer than 0.1 millimeter. So, from this graph like this many other things also you can find out. And this is actually the when it is a coarse particle, then we can do that way, but if it is a some soil, as I have mentioned that in the pan which is passed through 75 micron, if it is a soil particles is smaller than 75 micron, we will not be able to sieve it, and those particles actually if you want to sieve, then some amount will fly and volume will be waste, some amount will be lost, we will not be able to get the proper weight, and because of that those fine, when the soil contains both coarse and fine particles, then the classification will be combination of the sieve analysis and then another analysis that is called hydrometer analysis. Hydrometer analysis, in that actually generally we take the principle of Stokes law, and in this there will be a hydrometer, that is called hydrometer. This is the hydrometer actually, there will be a bulb in it, and the total volume of the bulb is only based on this bulb from neck to this, and remaining portion volume is so small it can be ignored. And this is designed in such a way that if I put the hydrometer in a 1000 cc jar, calibrated jar, and this if I immerse in that soil, this will indicate the reading will indicate the density of that water. So, if you mix with some soil in it, then density will change and automatically this hydrometer will give different reading. So, that actually will be taken, and whatever characteristics we are giving, that it is at the center of the hydrometer, whatever characteristics actually giving actually here, and initially it was here, and when I immerse this hydrometer, it will be lifted by some amount, and then this will be lifted by here, and that amount can be calculated by this. So, by Stokes law, that equation for terminal velocity V t can be obtained like this, and diameter from the Stokes law you can obtain from this, and again based on those calculation I can find out the percent finer in terms of this, that is G s by G s minus 1 by 1 minus W s R plus C m minus C w plus minus C tau C t. So, what are those? This is actually I will take a certain amount of fine particles, mix in a water, make a uniform sediment, and that sediment I will put the hydrometer, and I will take the reading, hydrometer reading, and from that hydrometer doing some more calibration, I can do this calculation. The soil we are taking, that soil actually specific gravity to be determined, suppose G s, and amount of soil taken, that is W s, and hydrometer reading is suppose R, and C m is suppose meniscus correction, and C w is actually if I put it in a distilled water and put it in a sodium hexametaphosphite sodium something, some chemical we use actually, sodium hexametaphosphate we use actually as agent. That is actually this is based on the principle of Stokes law, and Stokes law actually applicable for a spherical particle, small spherical particles, and if it is a sometime if I put it in a suspension, the spherical particle will have tendency to cloak together and make a bigger particles, and in that case Stokes law will not be valid. So, because of that we sometime add chemical sodium metahexaphosphate, that one actually as a deflocculating agent, and because of that addition there will be some correction. So, distilled water reading we have to take, and temperature correction, all those, this is the original reading and these are the 3 corrections. After applying this correction, this value to be taken, then you can find out the percent finer, and diameter can be calculated from this and percent finer can be calculated from here. So, that means I am getting a portion of the curve from hydrometer analysis and portion of the curve from the grain size analysis, and these two to be connected, and then if I connect then I will get entire distribution from silt clay to sand gravel, and then it will give you the complete grain size distribution in the sample. So, this is the way actually. Of course, this hydrometer analysis, lot of calculation, lot of calibration work etc. is there. This thing can be discussed more in detail in the laboratory. Only thing I have just mentioned that is a part of classification combining sieve and hydrometer, these two together, that is hydrometer will be used for the particles which is finer than 75 microns and which is greater than 75 micron, that is sand and gravel will be done sieve analysis, and then both parts will be plotted in a single curve, and then we will get the complete curve for the sample. And then after plotting the curve, the plotting is same, percent finer versus particle size, and after doing that, after examining the curve, one can find out whether the soil is uniform or well graded or any other. So, that classification can be finally decided. I think we can stop here.